Today's lesson is taken from our textbook in lesson 4.5 as well as 4.6, and the topics are conditional probability, the multiplication rule, and independence. So starting off with the conditional probability, we have the probability that event B occurs given that event A occurs is called a conditional probability. It is denoted like this. So the probability of B given A. So you can see, as a reminder, we read this as the probability of B given A. So we also call A the given event. A is the given event. So example 1, when a balanced die is rolled once, 6 equally likely outcomes are possible. And we let event F equal a 5 is rolled and O equal the event that the die comes up odd. So to determine the probability of F, we're going to determine a few different probabilities. First, the probability of F. The probability that a 5 is rolled, the probability of F would be 1 in 6. The possible number of outcomes over the total number, or the frequency over the total number of possible outcomes, is 1 over 6, which is equal to 0.167. Next, we have the probability of event F given that O happened. So the probability that we get that we roll a 5 given that the roll is odd. We already know it's odd. What's the probability that we get a 5? So the probability of F given O is equal to the number of ways that that can happen divided by the total number of outcomes. So we have one way that we can get a 5 given that an odd, we get an odd. So there are 3 odds, 1, 3, and 5, and one of those is the 5. So that's 0.333. So what we see here then is, for our interpretation, given that the die comes up odd, there's a 33% chance I should say 33.3% of rolling a 5 right, and that was conditional. There was a condition there versus, or compared with a 16.7% chance, and that one is unconditional. So much higher likelihood if we already know that it comes up odd, which makes sense. And then we have the probability of event O getting an odd, given that we don't get an F, given that we don't get a 5. So the probability of O given not F is going to be equal to, again, the number of frequencies, that number of ways that it can occur over the total possible number of outcomes. How many total rolls are there that are not a 5? There's 5. All other possibilities other than 5. There's 5 chances. And how many of those would be odd? Well, given that we know it's not a 5, there's only 2 odds left to consider, 1 and 3. So that gives us a 0.4 chance. So in comparison then, you can see the contrast. Let's see. Given that the 5 is not rolled, so that is the event that not F occurs, the possible outcomes are the 5 shown. Are these the 5 possibilities? Would be the 1, oh, that's not a good die. 1, 2, 3, 4, and 6. So under these circumstances, event O, odd, can occur in 2 ways. So you can either have the 1 or the 3. So the conditional probability that the die comes up odd, we just talked about that part. So when we compare the unconditional probability that the die comes up odd, we get, what's the chances of getting an odd? It's 1 in 2, right? Or 0.5. So in contrast, there's less of a chance when we know that one of those odds is no longer an option. So we have, in the above example, we computed the conditional probabilities directly, meaning that we first obtained the new sample space. Determined by the given event. So the given event helped us determine our sample space, which became our denominator. And then using the new sample spaces, we calculated the possibilities in the usual manner. Sometimes we actually cannot determine the conditional probabilities. Directly, but we instead we need to compute them in terms of unconditional probabilities. So let's take a look at this table here. Should look familiar. Our ages and ranks of different faculty members at a college. And part A says determine the unconditional probabilities that the selected faculty member is in his or her 50s. So we go to the table and we go to the row that is 50s, and we see 253 out of 1,164, and we get 217 thousandths. So about 21.7% of the faculty is in their 50s. And then determine the conditional probability that the selected faculty member is in his or her 50s, given that an assistant professor is selected. So 50s, given that we already know an assistant professor is selected. So that would be 36 out of just 320. Which is 0.113. Here we have a rule that helps us navigate all types of conditional probability situations, and given event A and B are two events where probability of A is greater than 0, we know the probability of event B given event A would be the probability of them both happening divided by the probability of A happening. So looking at this third example, talking about marital status and gender, we have from America's Families and Living Arrangements, a publication of the U.S. Census Bureau. There's a joint probability distribution, or we have here our contingency table. We also call that a contingency table for the marital status of U.S. adults by gender. As shown in the table below, we used single to mean never married. And so we're going to suppose a U.S. adult is selected at random, determine the probability that an adult selected is divorced given they are male. So divorced given that they are male. So that would be the 0.044 divided by the 0.485. .091, or about 9.1%. And then also let's determine the probability that the adult is selected as a male given that they are divorced. So given that they are divorced, what is the probability that they are a male? So in this case, we would do the 0.044 divided by the 0.104 to get 0.423, about 42.3%. So quite a significant probability there. So the multiplication rule and independence is our next topic. And the multiplication rule and independence you would find in your textbook in section 4.6. And essentially what we're doing here is taking the conditional probability rule, which is probability of B given A equals probability of A and B over the probability of A. We're going to multiply both sides by probability of A. So when we multiply this side by the probability of A and this side by the probability of A, you can see what happens. And we just switch the two sides in order to look just like this rule right here. These two cancel out, so the probability of A and B equals the probability of A times the probability of B given that A occurs. So there you go, general multiplication rule. So we have gender of students. In Professor Weiss's Intro to Stats class, the number of males and females are shown in the frequency distribution presented in the table. 2 students are selected at random from the class. The first student selected is not returned to the class for possible reselection. That is, the sampling is without replacement. So find the probability that the first student selected is female and the second is a male. So first we're going to define 2 events. So we're going to let F1 equal the event the first student is female, and M2 equal the event the second student is male. So what we're trying to calculate is what are the chances that both of these happen. We're going to use the general multiplication rule. So we need to determine the probability of F1 and M2. So we need to find the probability of F1 times the probability of M2 given F1. That's taken straight from my formula here and applying my different events. So what is the probability of F1? So the probability, we need to determine these separately. Probability of F1, the probability that the first student selected is a female. Well, we have 23 females out of the 40, so just 23 out of 40. And then what is the probability that our second selection is a male, given the first selection was a female. So we have the number of males is not impacted. We still have 17 males, but now we're only selecting from 39 students. So we insert these into our equation, and we get that the probability of F1 and M2 is equal to the probability of F1 times the probability of M2 given F1. So 17 out of 39. And we get 0.251 or 25.1% chance. And lastly, statistical independence is one of the most important concepts in probability, so we're going to take a brief look at independent events. And there's a quick and easy way to figure out if two events are independent by applying this formula. So B is said to be independent of A if probability of B given A is equal to the probability of B. So what does that mean? Let's take a look using playing cards. Consider randomly selecting one card from a deck of 52 cards. So we're going to let each of these events be defined. F would be the event that you get a face card. K, you would be selecting a king, so F for face, K for king. H being the event of selecting a heart. Determine whether event K is independent of F. That's our first question. So, and then we're going to determine whether event K is independent of H. So going back up here, B is said to be independent of event A. So K, we're trying to determine if K is independent of event F. So K would be like our B, and then F would be like our A in terms of substituting into this formula. So we will need to know for both of these questions the probability of event K happening. So, probability of drawing a king, there are 12, how many kings are there? There's only 4 kings, 1 per suit, 4 out of 52, or 1 out of 13, which is a 0.077 chance. So now we know what we're comparing to. So let's look at then the probability of K given F happens. Now if this number ends up being 0.077, we know the two events are independent. So F, frequency over total, is going to be, so given that we have a face card, what are the chances that it is a king? Still 4 kings, but now the number of possibilities is 12. Or since we only are looking at face cards. So that's going to be 0.333, and since the probability of K given F does not equal the probability of K, event K cannot be considered independent of F. Alright, one more. Determine whether event K is independent of H. Again, if we can say that the probability of K given H is equal to 0.077, then we know K is independent of H. So, probability of getting a king, given that we draw a heart. So that would be how many hearts are there given that we are drawing, or kings are there given that we draw a heart. Remember, there are 13 hearts. There'd only be 1 king possible. And when we divide that out, we get 0.077, which we notice is equal to our probability of K that we found above. So since the probability of K given H equals the probability of K, we know event K is independent page. So we talked about a few different things today. We talked about conditional probabilities. So when we have more than one situation going on, we have a probability of an event given that another event is occurring, and we calculated some conditional probabilities. And then we discovered a rule for conditional probability, where we would find the overlap probability of A and B occurring given, divided by the probability of just the given event occurring. And then we talked about the multiplication rule and independence. So we talked about just deriving that formula for the general multiplication rule from the conditional probability rule. And then finding out if two events are independent. And that concludes our notes.